All right, guys. Welcome back to the second week's interactive session of the course Viscous Fluid Flow. Uh, so let's get started. So today, I think the attendance is very less, but nevertheless, we will begin the session in its time, which is basically 3 p.m. now, and hopefully people will join. So we will start this the second week's content, but before that, I'd just like to recapitulate what we saw in the previous week. So basically, in last week, we saw some problems. We solved some problems related to the Reynolds transport theorem. Uh, so we applied Reynolds transport theorem for calculating the rate at which a water level would rise for an inflowing tank. And then we eventually went on to derive an expression for the rate of change of that height h, which is a function of time with so eventually we saw how that h, which is basically a function of time, actually is related to the inlet velocities at the cross-sectional areas to the area of the tank. So this is something that this is where we applied the Reynolds transport theorem uh, for the mass conservation. Then we solved the second problem, which involved using the RTT for conservation of mass, and then using the RTT as well for the conservation of momentum, which basically gave us the expression for the force, as you can see here. So we basically found out a force acting on a card. So I think the diagram is somewhere here. So we found out a force acting on a card that is moving with some velocity vc, which is subjected to a jet that is being coming out of a nozzle, and the jet itself has a velocity vj. So this involves the use of RTT in both mass and the momentum conservation. Thereafter, we solved some problems corresponding to some fundamental definitions in fluid dynamics. For instance, we basically saw how to calculate the stream function given a velocity field in the Eulerian description, which is of this form. So we use the basic definition of the stream function, which looks something like this. And then we found out the what would be the stream function, and qualitatively saw some plots associated with this form of the stream function. Thereafter, I also gave a note which says that when we are defining a stream function, the continuity equation is trivially satisfied, and the very definition of the stream function is based on satisfying the continuity equation, and we quickly saw that, which is over here. And then we solved the problem that is related to the Eulerian and Lagrangian approach. This was a good problem that we solved. So initially what we were given is we were given the center line velocity of a converging nozzle, and the velocity field is actually given to us. We were asked to calculate the acceleration of a particle using an Eulerian approach that is moving along this center line, and then calculate the same acceleration using the Lagrangian approach. And eventually we cross-checked our results with the fact that at time x equal to 0, that maybe which is here, the Eulerian acceleration, so x equal to 0, at the Eulerian acceleration eventually is nothing but the Lagrangian acceleration at time t equals to 0. So this is something that we proved at the end of this exercise, which is basically this. So the Eulerian acceleration at x equals 0 came out as v1 square by L, where v1 and L are just mere constants, and the Lagrangian approach gave us also the same acceleration. So this was something that we did, and then we again we looked back into the definitions of incompressible and irrotational flows. We solved some problem associated with that, and finally ended the class with an MCQ. So this was something that we did in the last week. Uh, if someone have any doubts associated with that, I would basically wait for some more time. If you have any doubts, you can speak out, or you can just unmute yourself and raise the doubt, or you can just type in your chat box or anything like that. So basically, I'll wait here for, let's say, 2-3 minutes, and then we will start off with today's contents, which is basically based on solving the Navier-Stokes equation, as you can see from my screen. And so we will basically first of all understand the different terms in the Navier-Stokes equation, because eventually we will be solving them in some sample problems, which are known as the plane Couette flow problem and the plane Poiseuille flow problem. So this is the agenda for today. Before starting, I would wait here for some more time, and then I would start or go on with today's class. Meanwhile, I just write what we are supposed to do today. All right. So in today's class, we will start off with the Navier-Stokes equation. So as you have seen in this week's lecture series, so the Navier-Stokes equation, when we write the different terms, for instance, in let's say we are writing in vector notation. So the Navier-Stokes equation basically, one second. Oh, so yeah, so we were starting with the Navier-Stokes equations. So when written in vector form, the Navier-Stokes equation looks basically something like this. So it is rho times the total derivative of the velocity field v, where this v denotes the velocity field, and then on the right hand side, it's nothing but the gradient of the pressure term, so which is this basically the force due to pressure, plus the viscous term, which is basically mu times del square v, plus if there arises any body forces, it appears as the body force term. So as you can see, this is the famous Navier-Stokes equation, as you guys know, or as you guys have seen at least in this week's tutorial, this week's classes. So in this equation, basically there are four terms associated with this, and also, and remember always the Navier-Stokes equation is associated with the continuity equation, which when written for an incompressible flow looks something like this. That this you already know, which is basically the divergence of the velocity field is equal to zero. So this is the continuity equation, and the Navier-Stokes equation is always written in conjunction with the continuity equation. So before proceeding further, let us recapitulate what the different terms in this Navier-Stokes equations essentially mean. So can you tell me what this term basically signifies in the Navier-Stokes equation? So
Total derivative velocity.
You are right. So this is basically a total derivative of velocity. But do you know what this signifies? So physically, what does this signifies? Yeah. So as you said, this is basically, so you can write this total derivative dv by dt as basically the partial derivative, which is basically del v by del t plus v dot grad of the velocity field v. But this is the definition of the total derivative, as you have rightly pointed out. So this means, so this term is basically the temporal term, and this is the convective term, and together this is basically the total derivative, which is obviously correct. But physically, this term, what I was the answer I was looking for is that physically this term, which is rho times the total derivative of the velocity field, actually denotes the force due to inertia. So that's what I will write here. So this denotes the force due to inertia. Just one second, I'll just check if the recording is on or not. All right, so the recording is on. Okay. Yeah, so this term denotes the force due to inertia, as I was saying, the term rho times the material derivative of del v by del t. Can you tell me what this term actually signifies? So this is nothing but the gradient of the pressure field. So this term, as you can see, this signifies the force due to the pressure field. So you must appreciate that the Navier-Stokes equation is nothing but a force balance between certain terms that acts on a particle inside a control volume. Okay, so this term, so the first term that we saw, which is rho times the material derivative velocity, signifies the force due to inertia. The second term, which is basically the gradient of the pressure field, signifies the force due to pressure. So this is nothing but the force due to pressure. So in the same spirit, can you tell me what this term signifies? The dynamic velocity times the Laplacian of the dynamic viscosity times the Laplacian of the velocity field V.
Viscous force.
Exactly, exactly. So this term is
Positive to viscous.
exactly. So this is basically the viscous forces, which accounts for the viscosity of the fluid, or which arises due to the viscous nature of the fluid. And of course, this term is, as I have already said, this is basically the body force. All right. So if this is clear, I hope this is clear to all. I hope this is clear to everyone. Yeah, so I think someone joined. So what we were discussing is we were discussing the Navier-Stokes equation, which is basically this. This is very familiar to you guys, and this is basically the continuity equation. So what we were seeing is that we were trying to see the different terms associated in the Navier-Stokes equation, which are basically this. The first term is the force due to inertia. The second term is the force due to pressure, which is basically the pressure field that arises uh, which basically leads to the which so the pressure field essentially compresses the fluid control volume, and the force associated with that is basically reflected by this term minus gradient of pressure. This term is known as the viscous forces, and this rho times b, as I have said, is the body force if there arises in the field. For instance, certain instances like if we are if there is a water electrolyte solution, that means if there are ions in a water, for instance NaCl dissolved in water, and then we are applying an electric field. Then we are applying electric field and there are charged quantities present in a solvent, then the electric force, which is basically I will not go into the details of it, but the electric force that the ions, that the charged species would suffer in the presence of an external electric field is reflected by this body force term. For instance, if there is an applied electric field, then the electric force basically becomes del square phi grad phi. So this basically is reflected as the body force, where phi is the potential, is basically the electric potential. So we will not go into the details of this electric force, but yeah, this is an example of how body forces appears in the Navier-Stokes equation. So I would now point so I would now like to put forward a question here, that can you tell me from this Navier-Stokes equation and the continuity equation how many unknowns are actually we are solving for? So can you tell me? So my question is, this is the NS equations or the Navier-Stokes equation. This is the continuity equation. What are essentially the unknowns, or how many unknowns are there in these two equations? So does someone would if someone would like to give a try, you can speak out, or I'll just help you guys. Like
Three.
three. So
Then
okay. Three is actually not the correct answer, IOC. The reason behind is that think carefully. Uh, think carefully. It's not three. So here's the thing. So it's not
two
three.
only. Density is not. Okay.
Yeah. So you know it's not two as well. So I'll tell you the answer. See, in Cartesian coordinate, if I write this Navier-Stokes equation, I would basically, so this is a vector equation, right? As you can see, this is typically a vector equation, and this is a scalar equation. Of course, the continuity equation is a scalar equation. So in Cartesian coordinate, if I write the Navier-Stokes equation, so I would have three equations basically in the x, y, and z direction. So from that NS equations, I would end up in getting three equations if I write in the Cartesian or in any coordinate system, in any three-dimensional coordinate system. However, there is also one more equation which is basically the continuity equation. So the continuity equation is basically one more equation that we have. So the number of equations that we have is essentially four, and from the Navier-Stokes equation in Cartesian coordinate, we will have three unknown velocities, right? U, V, and W. So u is basically the velocity component in the x direction, v is basically the velocity component in the y direction, and so on and so forth. So from these equations, there are three unknowns. That is the three velocity fields in the x, y, and z direction, or in any other coordinate system that we are looking for. However, this pressure field is also unknown, right? We are also solving for the pressure field in the Navier-Stokes equation, because density, this viscosity, these are fluid properties and these are known to us. Similarly, the body force is also known to us, because if there is an electric field that is being applied, let's say for instance, then the electric potential can be calculated from some other equations. Or what I mean to say is that this rho times v is indirectly known to us, which gives us in finding three unknowns plus one pressure. Three velocities plus one pressure. So the total number of unknowns that we have from these two equations is actually four. The three velocity components and the pressure. So we have four equations as I write here. So we have four equations and we have four unknowns. So these four unknowns in Cartesian coordinate, if I write, and we'll basically be dealing, so most of the problems we will be dealing in Cartesian and cylindrical coordinates, although later at later part of the course we will look into something which is known as the spherical coordinate system, if time permits. So the four unknowns in the three-dimensional space, the four unknowns is the velocity fields u, v, and w. So these are nothing but the velocity fields associated with the velocity vector v, and pressure, of course, which is a scalar quantity. So is this clear? Like how many unknowns does the Navier-Stokes equations and the continuity have? So I hope this is clear. Does anyone have any question? Okay, very nice. Okay. So this is the like idea behind the Navier-Stokes equation. So quickly, I would basically I would basically like I'll basically show some special cases associated with this Navier-Stokes equation, and then we will proceed to solve certain problems. As I said in previous class as well, we will proceed very slowly. If you have any doubts, you can always feel free to like stop me at any point of time, or you can just put your doubts in the chat box or in any way. So the idea is we will look into the certain instances of this Navier-Stokes equation, certain special cases of this Navier-Stokes equation, and then try to solve two or three problems associated with this with this NS equation. So let us begin. So so I was telling, let's see some special cases of the equation that we saw. So first one, I would say that what happens when there is a static fluid. Okay. And what I mean by static fluid is that what happens if the velocity field is itself zero. So this is the definition of a static fluid. As you can see, the name suggests that the fluid is now stationary, which means that the velocity field is zero. So let's look what do we get if we put the velocity field to be equal to zero in the Navier-Stokes equation. So can you tell me which term drops out if we put the velocity field to be equal to zero? This is clearly evident, right? So can you tell me if I have the velocity field to be equal to zero? So I think that is just evident, right? So if I put v equal to 0, which means the viscous term will obviously drop out, and the total derivative of the velocity will also drop out, which means I just end up having a balance. I just end up having a balance between the pressure force due to the pressure gradient and the body force. Okay, so in the special case when the velocity field is 0, my Navier-Stokes equation simplifies to be minus grad times the pressure. Remember, this P is the pressure field, plus rho times B equals to 0. And if I simplify, this becomes minus, or this becomes gradient of pressure is basically rho times B, which means this says that whenever the fluid is static, so whenever there is a static fluid that is inside a container, then the pressure gradient would always be balanced by the body force. So can you think of a very nice and a good example and a very famous law of fluid mechanics that is associated with this special case? Can you think about this? Uh, there is a very famous law that we learned in an elementary fluid mechanics course in our BTech first or maybe in our BTech second year, that which is associated with this with the fact that the pressure gradient is always balanced by the body force whenever the fluid is stationary. Exactly, it's actually not hydrodynamic law; it's the hydrostatic law. Okay, that is very nice. I got your point, but it's actually the law of hydrostatics. For instance, let's look at this case. So if there is a container and I have a fluid and I have a static fluid inside a container, then the only body force that can act is the gravitational force, right? Which will be acting in basically the downward direction. Okay, so then this B becomes this B. So this B is actually the force per unit volume. So this B would basically become equals to G, and then what I would have is I would have gradient of pressure equals to rho times G. Okay, which is nothing but the law of hydrostatics, as you have rightly pointed out. So it is basically the law of hydrostatics. Okay, and to make things more familiar to you, so if so if I now, let's say for simplicity, I consider this direction to be my z direction, and this is sufficient for this problem, then the gradient of P would basically come out to be del P by del Z, and this should be minus because G actually essentially acts in the downward direction. Okay, which is basically the famous law of hydrostatics that you guys already know. And if I just integrate this in the Z direction, I would just end up getting P, which is basically a function of Z, will be rho Gz plus some constant, and of course there might be a minus. So as you can see, so the very assumption of the fact that if there is a static fluid gives us the law of hydrostatics, and we basically got that pressure varies as rho gz, as we have been repeatedly been like we have been repeatedly we repeatedly saw this form. So you guys are most familiar with this form of the law of hydrostatics. Okay, so this is the first example, and I hope like you would appreciate it. Like, so now as you can see, the ns equations are very general equations, and you can derive several certain special cases from these equations. Now let us look one more special case. So does anyone have a doubt here? I will finish this special case and then wait for some more time, and then you can put forward your doubt if you wish. So let's look at one more special cases, which is basically the assumption when the fluid is inviscid. Okay, let's look at this special case. So as the name suggests, the inviscid fluid assumption means that mu, which is basically the dynamic viscosity, that is equals to 0. So now, as evident, if mu becomes equals to 0, however, this time the fluid is not static, so we are considering a moving fluid. So if in this case mu becomes equals to 0, we end up getting this following equation. Just substitute mu equal to 0 in the Navier-Stokes equation, and you will end up getting this equation, which is basically rho times dv by dt is just minus gradient of the pressure plus rho times the body force. Okay, and b for, and we are just considering that there is only gravity in this problem, so we'll replace b by this acceleration due to gravity, which we will in general denote as g. Okay, so this equation, okay, this equation has also got a very special name. Can you tell me what is this equation?
Euler equation.
Exactly, this is basically the Euler's equation. So the Euler's equation is a special case of the Navier-Stokes equation if you are imposing the inviscid assumption. Now, one more very interesting conclusion we can draw from this. So if we integrate, although I will not show now because this is something that we have already learned in your fluid mechanics course, the undergraduate fluid mechanics course. If we integrate this, let's say this equation 1. So if we integrate 1 along a streamline, can you tell me what do we get? So what I mean to say is, if I integrate,
Bernoulli equation.
exactly, we get the Bernoulli's equation. That is very nice. So if we integrate this Euler's equation, so if we integrate this Euler's equation, let's say from along a streamline, this black line will denote a streamline from point, let's say 1 to 2. If we integrate this, so all you need to do is just pick up this equation, integrate this along a streamline whose elemental length is ds, integrate both these sides, then you will eventually end up getting the Bernoulli's equation, which basically looks, as you guys all know. So I will not show the math here. You can maybe try this at your home, and if you have any doubts, I will show you in the next class. So if you integrate this, we get the infamous Bernoulli's equation, which is basically in terms of, like, if we write in terms of head, it becomes P1 by rho g plus V1 square by 2g plus Z1 equal to P2 by rho g plus V2 square by 2g plus Z2, which is basically the Bernoulli's equation that you guys all know. So the differential form of this Bernoulli's equation is basically the Euler equation that is shown by this equation 1. Okay. Yes, yes, indeed. This is for steady state. That's a very good point. So this is a very good point, and I forgot to mention this. Integrate. So yes, you need to integrate this Euler's equation along a straight line and invoke the steady state assumption. Yes, that is good. That's a very good point. And yes, that is for a steady state. So you also are right here. So invoke steady state assumption if we want to get the Bernoulli's equation. However, although there is also a special case of a Bernoulli's equation which is known as the unsteady Bernoulli's equation, but that is not the scope of this course to speak on it. So we will always, so if we are to use the Bernoulli's equation, if required, we will use the steady form of the Bernoulli's equation. So yeah, so in the Euler's equation, if you want to get the steady form of the Bernoulli's equation, you need to invoke the steady state assumption. So the steady state assumption, as you know, is that any time derivative. So I believe you know what is the steady state assumption. So any time derivative of any variable, if that is equals to 0, this means that we are in a steady state scenario. Yeah. So this is the thing. So So this is the thing. So these are three special cases, as you have seen. First, the law of hydrostatic. Second, as you have seen. Second, the Euler's equation. So I will recapitulate what we seen. So imposing V equal to 0 in the NS equation gives us the law of hydrostatic, which says that there is a balance between this pressure gradient and the body force. Imposing the fact that mu is equal to 0, the implicit assumption, gives us the Euler equation, which again says that the pressure gradient and the body force are balanced by the inertia forces. And under a special case, when we treat the fluid to be so if we treat the fluid to be inviscid and we invoke the steady state assumption, we get the Bernoulli's equation when the Euler equation is integrated along a streamline. So these are the special cases that we saw. Uh, so that's the theory part that I want to cover, because this session is essentially not meant for dealing with theories. However, I felt this need to be highlighted, because this was not essentially done in the week's lecture. So I have highlighted that. So with this, I will start off with the problem, but I will wait here for a couple of minutes. If you have any doubts, you can ask me, or if you want to take any notes, you can take. I would wait here for a couple of minutes and then start off with a very good problem, as you can see. So I have not shown you the problem, but we will see it shortly. All right. All right, guys. If you uh, if you don't have any question, I hope everyone is clear up to this point. So these are very essential essence of, so okay, for viscous forces to be neglected, what about the gradient delta? Okay, so yeah, so I think I got your question. Let's understand. So what Purna Sai is suggesting is that for viscous forces to be neglected, what about the del square velocity? Okay, so that's a good question. So what he's asking is that, if I'm not wrong, what he's asking is that if there is a case when mu is basically not equal to 0, however del square v is 0. Okay, so I think that is what he's asking. So does that also auspice? So
Yes, sir.
yes, sir. Okay, yeah, I got it. What you're asking. Yeah, so let's think about it. So what he means to say is that let's now consider a case where mu is not equals to 0, but del square v is basically equals to 0. However, what that means is that if del square v is 0, if I want to write down this in the Cartesian coordinate system, let's say for the simplicity of the problem, this would be what? This would be del square u by del x squared, okay, plus and of course I'm writing it in the x direction. This will be del square u by del y squared plus del square q by del z square. Okay, so this means that you are saying that this term would basically be 0. So the only way what I can see, of course, if I'm writing this del square u by del v square, I'm writing this in the, let's say I'm writing this in the x direction, of course. Let's say I'm writing this in the x direction. That means that I am basically leaving out, so I basically have these terms, okay. So the only way that del square v could be 0 is that u has to be equals to 0, right? There is no other possible options for this form to be equals to 0. So I think we would just end up we just end up in a trivial case here. That means that the fluid itself is not moving. So then, so if I just, so you got my point, right? So del square v equal to 0 would just signify that the fluid itself would not move. Let's say in the x direction we are considering. So in that case, I think, so in that case, I think it would trivially mean that this term would also have, would also have to be 0, at least in the x direction that we are considering, let's say. So I would say that we would eventually end up in the law of hydrostatic itself. That's what I would say here. Okay. So the only way when del square v will be 0, the only way when del square v would be 0 is the case when the fluid would not move. Because u has to be equal to 0. There is no other form of this. So in mathematics, there is something which is known as the trivial solution. So del square v equal to 0, at least, so there is that, so it arises one solution, and that solution could be the trivial solution, which should mean we would end up getting the law of hydrostatic. So this is what I could think as of now. But yeah, that's a good point actually. uh, but yeah, this is something that I think. Okay, so all right guys, good questions. So keep throwing questions to me, like when you don't like when you have a doubt in your mind. So so if you have no other questions, we would start off with a very simple, but yet it's a very important problem, and we will see why this problem is important in terms of in terms of getting several insights into solving fluid mechanics problem. So what this problem says is that there is this physical picture where there are two channels shown by these red lines. The lower channel is basically fixed, as you can see, or channel or a plate, you can say anything. So the lower plate is basically fixed and the upper plate moves with some velocity u naught. Okay. And in addition to this, and in addition to this, we are also applying a pressure gradient basically in the x direction. Okay, which means that there is an additional pressure gradient which drives the flow from this high pressure region to the low pressure region, which is in x direction, in addition to the moment of the top plate. Okay, and the width of this system is taken as b. You can, for simplicity, you can take b equal to 1 or any values of b, that's up to you. So given this scenario, so I hope the system is clear. I will repeat again if you guys wish to understand more. So there is this plates. The upper plate moves with u naught, which of course moves. So since the upper plate moves with u naught and the fluid have some fluid bears the density rho. So the properties of the fluid is density rho and viscosity mu. Since the upper plate moves with u naught, it will also drag the layer of the fluid with it, which means that the fluid also will move with some velocity, which will of course not be u naught, I mean the bulk fluid. So we'll eventually find out, but it moves the fluid. Okay, and in addition to the movement of this top plate, we also have a pressure gradient that is being applied in this x direction axially. Okay, so if this is the system, so what the question is asking is, they are asking us to derive an expression for the velocity profile and find the volume flow rate. So once the velocity profile is known, we will find out the volume flow rate. So that's the later part. But first we need to find out the velocity profile of this problem. So I hope the problem is clear. So I would stop here for 1 or 2 minutes for you to like look at this problem and think about how you will go on and solve this. So we will solve this problem very systematically. Okay, starting from writing the assumptions and invoking the assumptions in the Navier-Stokes equation, and then eventually solving the Navier-Stokes equation subjected to the boundary conditions. We will see what the boundary conditions will be for this problem, and then finally using the boundary conditions, integrating the Navier-Stokes equation, we'll find out the velocity field. So that's the algorithm basically that we will follow. But and we will follow this extremely so we'll go on with this extremely slowly and hopefully you can understand the problem in a very systematic way. Okay, so if you are clear with the problem, and I hope you are of course you have seen the problem, so we will start off by writing the assumptions. So the first assumption is that, so I will state you the assumptions and then I will expect you to answer me certain questions so that we keep the session interactive. Okay, so I say that first we'll invoke the steady flow assumptions. Okay, and then we say that the flow is fully developed. We will see the consequences of this fully developed assumption. Third, we say that the flow is incompressible. Okay, fourth, we say that the width of the plate in z direction is very large. Okay, so these are the assumptions that I have given forward in this problem. So with these assumptions, we will now write the Navier-Stokes equation and try to simplify the Navier-Stokes equation using by invoking these assumptions. Okay. Of course, I will also say that there is no body force. So this is fine. There is no body force, and the flow is 1D in nature. So it's in 1D flow, which means, so the implication of a 1D flow is that the streamlines are nearly parallel. So the streamlines would basically look something like this. Okay. Nearly parallel with respect to the x-axis, of course. Alright guys. So with this, let us start to solve this problem. Okay. And I would require your feedback in multiple steps from here on. So we start off with the continuity equation. Okay, so can you tell me what the continuity equation would look like in if we want to solve this problem in the xy domain? So we will solve basically, so since there it's a plate, okay, we will solve this in the xy coordinate system, and I would as I have said, this is the coordinate system that we will follow. So the center, so the zero of the coordinate system is coinciding with the plate basically here. And as we move ahead, so what I mean to say is that y equal to h denotes the upper plate which is moving with some u0. So I hope the coordinate system is clear. You can choose the coordinate system here also, this up to you. In fact, you can solve this problem once again on your own by taking the coordinate system to be at the center of the plate. This is completely up to you, but I have chosen my coordinate system to be coinciding with the lower plate. Okay. So based on this, can you tell me what the continuity equation would look like? I think there is a lag in the screen. I don't know. Am I audible? Can you?
Yes, sir.
Oh, okay, okay, sure. Yeah. So can you tell me, like, if you wish to tell, can you tell me what the continuity equation would look like in the x direction?
Do you get x equal to 0?
Okay. Yeah, so you are right, but you just said the final answer of the problem. So we'll first write the continuity equation from the beginning. So the incompressible form of the you are right, by the way, that's not wrong, but we will derive that basically. So the incompressible form of the continuity equation states that the divergence of the velocity field is zero. Okay, this is because we are assuming the fluid to be we are assuming the fluid to be incompressible, which means that the divergence of velocity field is 0. And now, if I want to write this, so as you can see, this is in vector notation. So if I want to write this in the Cartesian coordinate system, it would be del u by del x plus del v by del y plus del w by del z. Okay, now the very assumption of the fact that we are considering an 1D flow means that v is equals to 0 and w is equals to 0, which now means that this del u by del x is equals to 0 from the continuity equation. That's fine. Del u by del x is equal to 0, it's fine. But can you tell me what does this mean? What does this imply? Okay, mathematically we found out that del u by del x is equals to 0. That is well and good. But what does this imply? So yeah, go on.
U is not a function of x.
Exactly.
U
This
is not a
implies
function of
that
x.
u, yes, exactly. This implies that u, okay, is not a function of x. And this very statement, although it seems very trivial, is actually very powerful, because you will see that it eventually reduces the complicated partial differential the Navier-Stokes equation is a partial differential equation, right? However, the very fact that u is not a function of x and u is a function of y only reduces the PDE, because the Navier-Stokes equation is a PDE, to an ODE. And if we reduce a PDE to an ODE, we can just invoke simple integration to solve that ODE. Okay, so that is basically the idea, that u is now not a function of x. That is well and good. So this means therefore u has to be a function of y only. Okay, all right. So the second step, so for the second step, I would name this as 2, I would name this as 1. So in the second step, I don't know, but there is a lag in my screen. I'm sorry for that. I'm moving my screen basically, but it's just saying. So just 1 second, guys. Okay, I think it's here. Okay, sorry for that. All right. So in the second step, we begin by writing the x momentum equation. Okay, or we are writing a Navier-Stokes equation in the x direction. So let us do this systematically. So if I write the Navier-Stokes equation in the x direction, the inertia term comes out to be rho times del u by del t plus u times del u by del x, which is basically the convected term, plus v times del u by del y plus w times del u by del z, and this is equal to the pressure gradient, which is minus dp by dx, that is, since there is a pressure gradient applied in the x direction from the problem that we saw, plus mu times del square u by del x squared plus del square u by del y squared plus del square u by del z square, and we are disregarding any body force term. Okay, so now let's simplify this, and we will eventually see that we just end up getting an ODE. Okay, let's simplify it. So can you tell me what this term would be? What basically this term would be? Del u by del t?
0.
Yeah, exactly. Why 0? Because it's steady, right? We have invoked the steady state assumption. So this is basically because of the steady state assumption. We saw that del u by del x is 0, because u is not a function of x, and hence this term, this del u by del x is 0, that we already saw from the continuity equation. V is 0 because we are assuming the flow to be one directional. That means the streamlines are parallel to the x direction, which means that there is no cross flow across this streamline, and that's why V and W are of course 0. Okay, then since del u by del x is 0, its derivative with respect to the x direction will also has to be 0. This is because since del u by del x is 0, and since the jet direction is infinitely very large, as we have said that the width of the plate is very large, its derivative with respect to jet would also end up to be 0. Okay, and that's why del square u by del z square is also equals to 0, which means that a jet direction that the plate width is very large with respect to the channel height. Okay, so the consequence of this del square u by del z square equal to 0 is because the fact that the plate width is very large. So we end up getting the left hand side to be just 0, and then we have just minus dp by dx plus mu times del square u by del y square. Now, as we have already said, since u is just a function of x only, which means I can now write this partial differential form. I can write this partial differential equation into d square u by dy square. That is simply because u is just a function of y. Okay, which means I end up getting mu times, or I end up getting d square u by dy square equals to 1 by mu times dp dx. So as you can see, again I think there is this lag. I'm really sorry for this, guys, but I just can't help. Maybe this is due to some internet issues over here. Yeah, okay. So as you can see, there is, so in this case, so can you tell me in this case, where is this balance of force coming from? So which forces are basically balancing whom? Can you tell me? From this equation, the simplified form of the Navier-Stokes equation in x direction. So I think one term is trivial. This term is basically trivial. So I mean, you should basically tell me like, so where is this balance of force? So which force is basically balancing whom in this equation? Like, can you give it a try? Discuss for, yeah, exactly. So as you can see, the pressure gradient, which is basically the applied pressure gradient in the x direction, is being balanced by the viscous forces. Okay, so that is the essence of actually starting from the complete Navier-Stokes equation, invoke the assumptions, and then simplify it to actually know what the picture is being showed in this problem. Okay, so now the next step. Okay, before proceeding, before like integrating this equation and getting the result, let us also try to see what happens if we apply these same assumptions in the y momentum equation. Okay, let's see what do we get. So now if I apply this in the y momentum equation, so let us now write the y momentum equation. So the y momentum, so I'll just write this fast because we already know how to write the ns equations in various coordinate systems. So the y direction velocity is v, so that's why I'll write del v by del t plus u times del v by del x plus v times del v by del y plus w times del v by del z equals to minus del p by del y plus, okay, there would be a row here. There would be a row here. Okay, and this is mu times del square v by del x squared plus del squared v by del y squared plus del squared v del z squared. Okay, and I'm disregarding any body forces, as you can see. So quickly I will show you that if I invoke the fact that there is the velocity is just one direction and we have just the x direction velocity, means that v has to be 0. So this v is 0, this is all 0, as you can see, because v is 0, and these are just zeros, which means that we just end up getting del p by del y is equals to 0. Okay, so this means that, this signifies the fact that the pressure in this case, at least in a 1D flow, does not vary in the y direction. Okay, and this is obvious because had there been any pressure, gradient in the cross flow direction, this means that the fluid would also move in the cross in the cross direction. Okay, which now means that our assumption that the flow is 1D remains invalid. I would again repeat, the consequence of the fact that del p by del y is 0 again lies because had del p by del y not been equals to 0, okay, this means that there would now be a fluid flow in the y direction, and that would not be possible because we are invoking the 1D assumption. Okay, so this is the consequences of the y momentum equation. And now similarly you can similarly show that similarly I would write that from the z momentum equation you can show that del p by del z is also equals to 0. Okay, all right. Before proceeding, does anyone have any doubt here? Okay. So I hope this is clear. So if you don't have any doubt, let us now integrate equation 1. Okay. So equation 1 as we got, so I'll write down that again for your convenience. So it was what? It was d square u by dy square equal to 1 by mu times dp dx. Okay. So now what we will do is we'll integrate this, integrate with respect to, let's say with respect to y. So if we do that, we would get du by dy equals to 1 by mu times dp dx times y plus c1. And then again, if we integrate it again, if we integrate again, what we would get is we would eventually get u as a function of y is just 1. Okay, so did I write this correctly? I think it does. Okay, so what we would get is 1 by 2 mu dp dx times y square plus c1y plus c2. Okay, so this is something that we got by integrating twice with respect to the y direction. I hope this is clear to you because I believe you have done this many a times. All right. Okay. So now so how do we now calculate C1 and C2? So because we need, so for the velocity profile, so remember our task is to evaluate the x direction velocity profile. Okay, and for that we need to evaluate the constants C1 and C2, which are constants but these are unknown. So how do we now evaluate this C1, C2? Can anybody tell me?
Boundary conditions.
Exactly, from the boundary conditions. So we'll now use the boundary conditions. So the first boundary condition, let's see what would be the first boundary condition is. So the first boundary condition is the fact that the lower plate is fixed. So if the lower plate is fixed, the fluid layer that is just adhering to this lower plate, which is just above this lower plate, will also not move. Which means we can invoke the no slip boundary condition here, and the no slip boundary condition would basically look like something like this. So, okay, so at y equals to 0, u at y equals to 0 is equals to 0, and this is due to the no slip boundary condition. Okay, which means that if I now invoke y equals to 0 where I will simply, so if I put y equal to 0, this term would go to 0, this term would go to 0, and u is also 0 because of the no slip. So which means you can show that C2 eventually come out to be equals to 0. Okay, so this is the first boundary condition. Can you tell me what the second boundary condition would be for this case?
U at y equal to h is u naught.
Exactly. By the way, yes, exactly, you were right. At y equals to h, u at y equal to h is u naught. That is fine. But before this, I just want to ask you a question here. Okay. So, what is the order of this differential equation? So, you know this is an ordinary differential
Second
equation.
order.
Yeah, it's second order, exactly. So, since this is a second order ODE, we require at least two boundary conditions. We require at least, so what I mean to say is that at least two boundary conditions are needed, and that's why we invoke these two boundary conditions at u equals to 0 at u equal at y equals to 0 and at y equals to h. Okay, all right. So now, as IUC rightly said, if I apply the fact that the upper plate is actually moving towards right with u naught, I end up getting u at y equal to h equals to 0. And if I apply this boundary condition, let's see what do we get. So all you need to do is we just need to put y equal to h in this equation, keeping in mind that C2 is 0 because we found out. We will end up getting something like this. U naught, you may also try it at your end. We'll end up getting something like this. U naught equal to 1 by 2 mu dp dx times h square plus c1h. The idea is to calculate c1. So we will bring c1 to the left hand side and divide the entire equation by h. So we will get it to be u naught by h minus 1 by 2 mu times of dp dx times a. So C1 is found out. So since we know C1, all you need to do is just substitute the value of C1 and C2 into the equation 1, which is basically this equation. Substitute the value of C1 and C2 in equation 1. C1 is this, C2 is basically 0. So we'll substitute this. So what we will get is, let's substitute. We'll get u as a function of y will basically be 1 upon 2 mu dp dx times of y squared plus c1. So c1 is basically u naught by h minus 1 by 2 mu dp times dx times h. Okay, times there is an y, so there would be an y here. And if I rearrange this equation, okay, I'll just do a certain rearrangement of this equation. It can be written as, so I'll just basically bring this term outside and club this term and this term. Okay, so I would get, so what do I get? I get u naught times y by h as one term plus, if I take, so I'm just clubbing this term and this term, taking 1 by 2 mu dp dx as common. So I would get 1 upon 2 mu times dp dx into y square. So what I would get it, I'll get y square minus y by h maybe. Please check the algebra, and if I am wrong, please correct me. Okay. Now here, so is everything clear up to this point? Okay, I would stop here. So our first task is done. So this is basically the velocity profile in the x direction, which is basically a function of y. Okay, so this is the first task that we are supposed to do. However, I'll give you some qualitative insights of this expression that we got. Okay, and I feel that these insights are very much important as like doing the math and getting the result. Okay, so if you have any doubts, please let me know. All right, now let's see. Now I'll try to give you some qualitative insights of this expression that we got. Okay, so so what I would do is I would name this part, this u naught y by h as term A. Okay, and this part 1 by 2 mu dp dx into y square minus yh as term B. Okay, and now let's see. So if I consider one case, if I now consider one case where there is a flow, okay, where there is a flow of fluid in, let's say, the x direction. Of course my x direction is this. Okay, there is a flow of fluid from left to right in the x direction. However, now I choose dp dx to be equals to 0. That means there is no pressure gradient, and the top plate moves with some velocity u naught. And this particular problem is famously known as the Couette flow. Okay, so in that case, as you all know, the velocity profile. So can you tell me what is the velocity profile in this case? What is the nature of the velocity profile in this case? So this is something that we have done. Yes, tell me.
Linear.
Exactly.
Linear.
Linear. So this velocity profile would just be u naught times y by h. So this is just one case. Okay. In the second case, I would say that now let us consider a case when the upper plate and the lower plates are fixed. Okay, which means u naught is not there, which means u naught is equals to 0. However, I impose an axial pressure gradient, this would be minus dp dx. So now I impose an axial pressure gradient in the x direction, of course, which is non-zero with some value minus of dp dx. Okay. In this case, can you tell me what is the velocity profile, or can you at least qualitatively tell me what is the velocity profile? What is the nature of the velocity profile?
Parabolic.
Parabolic. And if you see, the velocity profile would simply end up so we'll simply end up getting this form of the velocity profile, the term b. Okay, so it would be 1 by 2 mu times of dp by dx into y square minus yh. Okay, of course I need to consider my axis at the bottom plate. Okay, this is important. So this is my axis that we'll be considering. All right, so did you see, so before, like, I'll I would like to put into something that I was trying to say. This problem, the first problem, is known as the Couette flow problem. This is known as the Couette flow, and this problem is known as the plane Poiseuille flow. So did you see that the answer that we got here is basically a linear superposition of the answer for the plane for the Couette flow problem and the plane Poiseuille flow problem, which means that I can write that this u as a function of y is the solution when there is a Couette flow plus u of the plane Poiseuille flow. This means that instead of solving the entire Navier-Stokes equation, you can simply say that if I separately solve the Couette flow problem and if I separately solve the plane Poiseuille flow problem, okay, and I separately get their velocity field, then the velocity field for this combined Couette flow and a Poiseuille problem is basically a linear superposition of these two like solutions. Okay, this is known as the linear superposition, as I have already said, and you need to understand that this is possible because the governing equations which is basically, so what was our governing equation? So this was our governing equations is linear in nature. So this is the hallmark of a linear governing equation, and if our governing equations are linear, we can stitch the equations of the individual problem and then get the answer of the combined problem. Okay, so this is the qualitative idea that I want to give you, and I hope this is clear. However, if I have my inertia terms in the Navier-Stokes equation, the inertia term essentially adds to its non-linearity, which means that the linear superposition technique that I showed you here will not hold good. Okay, so if your governing equation is linear, you can always use the method of superposition. That is something that I want to put forward here. Okay, so I will write that down for you to be like absolutely clear of what I was trying to say. If the governing equations are linear, I mean, we can use the method of superposition. All right. Okay, so is this clear to everybody or not? So this is the first part of the answer that we did, and I hope this is clear. However, before moving into calculating the volume flow rate, I will again wait here for some more time. Okay, and you can write down, or you can, like, if you want to take some notes, you can write it down. Okay, and we will start the second part. All right, guys, now let us calculate the volume flow rate if you don't have any questions. So we'll write, so what we do is we'll calculate the volume flow rate now. Calculating the volume flow rate. Okay, so so does anyone have any idea how we can calculate the volume flow rate? I will draw the figure once again for you to be clear. How do we calculate the volume flow rate? Does anyone have any idea? Given we know the velocity field now. So again, given we know how the velocity field looks like, can you tell me how do we calculate the volume flow rate?
Integral u dA into width.
Exactly. Exactly. So what she said is, we will take, so these are the plates. The lower plate is of course fixed. The upper plate is moving with some u naught. So what we will do is, we will take a, so we'll take a finite length y, take a fluid element which will basically look something like this. We'll take a fluid element of thickness, we'll take a fluid element of thickness dy, okay, which will basically look something like this. So the thickness of this fluid element is of course dy, and of course this width, as I have said, this width is b. Okay, so what we will try to look is, we'll try to look through this elemental area b dy, the amount of fluid that will basically pass through it, and then integrate it over the entire cross section to get the entire volume flow rate. Okay, so what so as IUC said, she was absolutely right. So the volume flow rate q would be the elemental volume flow rate through this area. So the elemental volume flow rate would be ui, which is the velocity, times b dy. Okay, because b dy is basically the area. So the velocity times the area would basically give us the volume flow rate, and then integrate it over the entire length of the channel, which is basically from 0 to h. Okay. So we just need to do this integration. So this is basically the volume flow rate. So this is the volume flow rate. So now we know the expression of u of y. So this is basically the expression of u of y. We just need to do this calculation. So let's do this. Let's do some math as well. So we just need to substitute this u of y and then integrate this. So what would this q look like? Let's see. So q would be integral of u of y, and u of y looks something like this: u naught y by h, if I'm not wrong, plus 1 upon 2 mu dp dx into y square minus yh, and of course this is u of y. We need to multiply with b dy, where b is basically the weight. So let's do this integration. So I think you guys also like are masters of integration now. So let's do this. So the first term would be what? First term would be u naught y squared by 2h. This will vary from 0 to h, of course. Then this term would be 1 by 2 mu dp dx. This would be what? Y cubed by 3, right? So this would directly be y cubed by 3. This will vary from 0 to h, minus this would be y squared by 2 varying from 0 to h times h, and then this would be b times dy. Please check my math. I like if I might be wrong as well at some point. So then let's do this. So this term would eventually simplify to be u naught times h by 2 maybe, plus this term would be what? It would be 1 by 2 mu. It would be h cubed by 3 to be precise. Okay. This would be 1 by 2 mu dp dx times h cubed by 3 minus this term would give us what? It would give us h cubed by it would give us h cubed by 2, I think. Yeah. It would give us h cubed by 2. Okay. ठीक है? And of course there is this bracket. So this would be what? This would be b times, let's do this, u naught h by 2 plus 1 upon 2 mu, okay, times of dp dx times this h cubed by 3 minus h cubed by 2 will give us what? It will give us h cubed by 6. All right, it will give us h cubed by 6. And then if you simplify, you just simplify, you will eventually get the volume flow rate to be q, which will be equal to u naught h b by 2 plus 1 upon 2 mu dp dx into h cube by 6. So that's it. That's the answer of the volume flow rate. Okay. All right. So this is the answer that we got for for the volume flow rate, and this is the final answer that we are looking for. Okay. So we just need to do this integration, and I hope this is clear for to everybody. So again, I'll wait here for some more time. If you have any doubts in this answer or anyway anywhere in this problem, you can feel free to unmute and speak out. And then I will just start with another problem. So I'll again wait here for 1 or 2 minutes. Almost. So does anyone have any doubt here? The calculation of volume flow rate and the overall answer to this problem. Again, before like going
One
into, yeah,
neg
yeah, tell me.
the negative will come before dp by dx.
Where
Final volume flow rate.
there should be negative for what? Okay, okay, yeah,
Second
yeah,
time.
yeah, 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 I got it. So, yeah, yeah, so this would be h. Okay. So yes, 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 exactly. There will be a negative because this term would be negative because h cube by 3 is less than h cube by 2. Yeah, yeah, very good, yeah. Thank you for the correction. So there will be a negative sign, okay, which is basically the negative. Okay. ठीक है, good. So I was just thinking about this. So this means that there is also so based on this result, actually I was just thinking it now, that if I now have u naught to be equals to, so let's do this thing, okay. So let's now consider a special case. So that is actually a very good point you said. A special thing just rang into my mind. I'll just tell you. So if I now consider a special case where q is equals to 0. So by some means that I have enforced the condition that the volume flow rate is 0. Okay, this means that u naught h times v by 2 should be equal to 1 by 2 mu dp dx times h cube by 6. Okay, which means which means that, okay, let's simplify this. So this 2 and 2 cancels out and this h cancels out. So this means u naught, let's see what we get. So I get u naught be 1 by 2, oops, 1 by 6 mu b times dp dx times h square. So what I was trying to think is, if I somehow tune my velocity and the pressure gradient into this relation, if I somehow tune my velocity, so because u naught we are applying, okay, that we can control how the second plate moves, okay, and we can also control the value of this dp dx, okay, and if I can tune this, then I will reach a point where the volume flow rate, okay, where the volume flow rate will be 0. You understand that, right? But physically, can you think of this problem that even if I tune my u naught and dpdx to be certain values that they follow this relation, okay, this means that the volume flow rate is 0. But does this mean, my question is, does this mean that the flow field is 0 everywhere? So this looks very interesting, right? So can you tell me, like, Did you understand my question? What I was trying to say, that okay, now I consider a special case where I have q equals to 0, which means that u naught and dp dx are now related by this manner. Okay, so this means that q is 0 right now. However, does this mean that that the velocity field is 0 everywhere? That is my question. Does anyone have a like answer to this, or like? So think about this. This is a very actually this is a very interesting point. Think about this. Maybe so this essentially should not mean that u of y should be 0 everywhere. Okay, this just means that the average velocity can be equals to 0 because the volume flow rate is calculated from the average velocity. So the average velocity might end up to be 0, but this does not mean that the fluid particles or the individual fluid elements at each and every point should essentially be equals to 0. Okay, this is something that I am thinking of right now. But yeah, that's a very important one. That's a good point that we can maybe deal, or we can think about this. Okay, all right. So if you don't have any doubts, let's solve one more problem and then maybe we will call it a day, because like solving at a stretch 2 hours, like it's little bit hectic. We might have some interactions if like students feel, but like we will not and like stretch it very long. So yeah, so yeah, if you have any doubts, you can of course like post it here, or you can post it in the discussion forum. As I have said, these sessions are recorded and will be live on YouTube. The lecture notes will also be provided in the course website. Okay. Okay, guys. So let's now solve one more problem. This is a very simple problem and it's not that long as the previous problem. So what we need to do is, this is again a Couette flow problem and it's basically some numerical uh, results that we need to find out. So the special case again where the upper plate now moves with some velocity u that is given, okay, and the height of the channel is given to be equal to 1.8 centimeter. So what they're asking is to calculate the shear stress at the upper and lower wall. Okay. Yeah, so they're asking us to, if this is the flow scenario, they're asking us to calculate the shear stress. So can you tell me how do we calculate the shear stress here?
Mu dou u by dou y
Yeah,
for
exactly.
Newtonian fluids.
Yeah, exactly. So the shear stress here, that will be tau xy. Okay, because remember stress is essentially a tensor. That's why we write it in this form. So stress is basically written in index notation. Stress is written as tau ij, where the one component denotes the direction and the other component denotes the plane. And in xy plane, that's why we write stress as tau xy. And in general, if we follow the Newton's law of viscosity, it is nothing but mu times del, as you have rightly said, it is nothing but mu times del u by del y plus del v by del x. Okay, because I'll tell you why is this so, why this extra term del v by del x essentially come. However, this will go out to be equal to 0 here. But remember that stress, which is basically a tensor, it is always written as mu times, this is known as dyadic of velocity plus dyadic of velocity transpose. Remember, this del v is not, this is not a scalar, this is not a vector, this is known as a dyadic product. If you follow Einstein's, so there is something known as Einstein's convention or Einstein's summation. So there is known as something known as index notation, and if you follow index notation and follow that Einstein's rule, this dyadic of velocity essentially can be written as del uy by del xj. Okay, and this stress in Einstein's notation is written as tau ij, and this dyadic of velocity transpose is written as del uj by del xi. Okay, so these are some extra information that I'm just giving to you. But yeah, so what I mean to say is that uh, so what Einstein's rule says that if there are two free indices, which is basically this I and j, because these are not repeating, so if there are two free indices, it denotes a tensor, which is basically this ij. So this dyadic of velocity, since the left hand side is a tensor, the right hand side is also is bound to be a tensor, which means this dyadic of velocity is essentially a tensor product. Okay, so this is the idea. However, in the xy plane, this gets simplifies to just this term, and in this case, since the flow is one dimensional, because this is a simple Couette flow, this v essentially goes to be equals to 0. which means I just end up, as you have rightly said, as tau xy is just mu times del u by del y. Now, what is this u? Because u is also not given in your problem. Can you tell me what is this u? So we just saw this some while ago. Yeah, tell me.
Uh, Couette flow
Yeah,
problem.
Poiseuille
U
problem. So it
by
is
y.
just exactly. So it is just
UH.
u naught times y by h, right?
Yeah.
So del u by del y can also be written as du by dy because u is just now a function of y, and this just becomes u naught by h, which means this tau xy, that is the stress, is basically mu times u naught by h. Okay, and since mu is a constant, okay, u naught is a constant because u naught is just the velocity of the plate, u naught or u, because I think I have just written u here. Let's write it as u naught for keeping the symbols similar. So since mu is a constant, it's just a fluid property, u naught is a constant and h is a constant, which means that the stress field for this Couette flow is like uniform throughout. So, okay, so this means that the stress field is uniform. That's what I would say. The stress field is uniform. Okay, which means the wall shear stress will also be equal to this tau xy, and this is just tau w. That's it. So this is basically the formula of the wall shear stress, or the wall shear stress that the question is actually asking us to solve for. Okay. Uh, I hope this is clear. This is a very easy problem. I hope this is clear. So
Yes,
again,
yes.
yeah, okay. So I was actually starting to start one more problem, but we will not start this problem today because this is a bit a long problem and this would make this thing a little bit stretching and monotonous. So we will start this problem in the next class. However, if you have any doubts, I'm here for let's say 5-10 minutes. If you have any doubts, you can tell me. We will again recapitulate what we learned today, and then we will maybe call it a day now. So yes, addressing your doubts, I would quickly recapitulate what we did today. So we basically started off with the Navier-Stokes equation. Okay, so started off with this Navier-Stokes equation, and then we saw how many unknowns do we need to answer in this Navier-Stokes equation. Then ran into some special cases. For instance, the law of hydrostatics that we saw, and we saw something which is known as the Euler equation by invoking the assumption that mu is equals to 0, that is the dynamic viscosity is 0, or or in other words, the fluid is inviscid. Then I say that if we integrate this Euler's equation along a streamline and invoke the fact that the fluid is steady, we get what we know as the Bernoulli's equation. And then this was something that we saw. Then we solved the problem. This was an extensive problem that we saw. We went through this problem very systematically. So this problem involves calculating the velocity field by solving the Navier-Stokes equation. And the physical picture is something like this. So the upper plate moves with some velocity u naught, and there is an applied pressure gradient in the x direction. The fluid bears a property density which is rho, and the dynamic viscosity mu, and the height of the channel is h. Okay, we were asked to find out the velocity profile, and these are the assumptions that we saw. So for instance, the important assumptions of the so the consequence of this fully developed assumption, the steady flow assumption, incompressible assumptions, these are something that we saw. The 1D flow assumption. Okay, so we started off with the continuity equation, solved the x momentum equation, invoked all the assumptions, and then we eventually saw that the equation reduces into an ODE of order 2. We used two boundary conditions to find out the exact form of the velocity field u of y. And then we saw a very important principle which is known as the principle of linearity. This is basically the fact that if your governing equations are linear, okay, if your governing equations are linear, you can always superimpose certain problems. If you are asked to find out the answer of a more complicated and an involved problem, you can superimpose the answers of the simpler problem. Okay, that is something that we saw. However, this is, as I say, this is not possible if the governing equations are non-linear. For instance, if you have the inertia term in the Navier-Stokes equation, you cannot use the principle of superposition. And then we calculate the volume flow rate, which is basically integrating the velocity by taking an elemental strip of area b times dy, and then calculate what is the volume of fluid or the chunk of fluid that will pass through this elemental area. Then integrate it along the height will give us the volume flow rate. And then we solved and then we also saw a very interesting case. Actually, I didn't think about it initially, that what if q is 0, do we get a special relationship between u naught and dp by dx? And indeed we get this. But this essentially, to me at least, this essentially doesn't mean that although the volume flow rate is 0, the fluid flow field will not be 0 throughout. uh, but however, the average velocity, if we just calculate the average velocity by taking that cross section for this particular relation of u naught and dp by dx, the volume flow rate would come out to be 0. uh, and then we solved a very simple problem of calculating the shear stress. In fact, the calculating the wall shear stress of a simple Couette problem. And yeah, so we will, so this third problem, so I'll just briefly, yes, put this third problem into the picture, and then we will solve this in the next class. So this is the fact that there is a belt which is basically moving with some velocity u naught, and this belt actually drags a stationary fluid which basically gets attached to the belt, and when the belt moves, the fluid is also dragged upward by the belt. So given these conditions, okay, they are asking us and also using the fact that the belt length is infinitely long, they are asking us to essentially calculate what will be the velocity profile. This is a very similar exercise. You can also try. We will briefly go through this problem in the next class before starting the next class agenda. But yeah, so the idea again is that we will solve the Navier-Stokes equation. However, now there is a body force term that will come into the picture because of the effect of gravity, and of course this will again have certain interesting implications. All right, so we will stop here. If you have any doubts, you can ask me, or we will stop. We will end today's class. Thank you once again, everyone, for joining. Uh, we will again meet maybe in the next week. Yes, of course, we'll meet in the next week at the same time and discuss more problems involving the Navier-Stokes equations, and then move into some cylindrical geometries, if possible, maybe some spherical geometries or things like that. All right. If you don't, if you don't have any doubts, maybe we'll call it a day today. I hope you have learned something from this session. Thank you again for joining. Uh, so yeah, yeah. Go ahead, IOC.
Okay.
Do you have any
No, no,
doubts?
no, no. No, no. Thank you.
Yeah, sure. Okay. Thank you very much. So I'm ending this session.